All right. Good morning, everybody. Good afternoon, whatever it is that you are watching this video. This is the law of conservation part two. So hopefully you've watched part one and you've done your ad puzzle because that's going to help you out a whole lot in understanding the information I'll be sharing with you guys today. About that information, we're looking at the law of conservation of mass. And a lot of times everyone's kind of asking, well, what does it really mean in simple terms? Well, once again, the law of conservation of mass is sometimes also called the law of conservation of matter. And all it's saying is that whatever you begin with, you should end with. Because here's the reason why matter cannot be created or destroyed. So whatever you start with, you should end with. Now, vocabulary here is super important. And we won't say beginning and ending. We're going to use the proper chemical terms. And the proper chemical terms for your beginning would be the word reactants. These are what you put in to your chemical reaction. Think of them like your ingredients in baking a cake. That's what you begin with. And we're saying that the amount of what you begin with, that's this word total mass, must equal the total mass of what you end with. Okay, what you begin with, reactants, must be what you end with because matter cannot be created or destroyed. Now, when we're getting deeper in vocabulary, we get to understand what you're reading. And so if you're looking at all of these questions, they all have a chemical formula. And I covered this a little bit in the video yesterday, but in the formula, it's telling you your ingredients. In other words, it's telling you your ingredients, your reactants, and your product. So in this chemical formula, to make water, we have to add hydrogen and oxygen. That's what the H and the O stands for. But like when baking a cake, you have how much sugar, how much flour. Well, you not only need sugar and flour, because that doesn't really help you. You got to know how much of each of those you need. And I need 2 molecules of hydrogen gas, okay? And I need 1 molecule of oxygen. Now, you might say where the one comes from, but if you remember in yesterday's lesson, we said we don't write the number one in chemistry. So the one is understood. So I need 2 of H2 and 1O2, and that will give me 2 molecules of water. And so understanding what you're reading, understanding what your formulas are and your elements are going to make this lesson a little bit easier to sort of comprehend. So here are all of your important vocabulary words sort of comprised on one page. The reactants are what you have at the beginning, do, and your products are what you have when the reaction is complete or ending. Now, how to read those chemical formulas? We said yesterday that your subscripts, which means your underwriting, they come directly behind a element, and they tell you how much atoms are present. So there are 2 hydrogen, but here we have a coefficient. And we said yesterday, coefficient multiplies uh, how much molecules you have. So we're going to say 2 times 2 equals 4. So there are 4 individual, okay? There are 4 individual types of chemical reactions, okay? So, and so we have 4 of these guys, all right? And the next thing would be, well, how much of the other guys do we have? Well, we have 2 oxygen, and because there is no coefficient, we're going to just say, hey, that's 2. So on my reactant sides, here's this plus sign that's going to be super important. So my total mass, so you have to add these up at the end. So 4 plus 2 is 6. So now I'm saying that now I have 6 total atoms on my reactant side. Now, if what I just said is true, the total mass of your reactants must equal the total mass of your products. So let's see if that's true. So once again, how many hydrogens do I have? 2 times 2 is 4. Okay, that's looking good again. Now, because now the hydrogen and the oxygen are combined, this coefficient multiplies everything behind it. So I must say now 2 times the 1. Remember, the 1 is in there, but it's understood. So 4 plus 2, and once again equals 6. So I can now prove the law of conservation of mass. It's now telling me that when I add up, even though it looks different over here, that by the time I add them and combine them in this chemical reaction, whatever I began with, my reactants, will equal whatever I end with on my products. Oh, hopefully a light bulb went off in your head and sparkles and fireworks. Okay, so that's, even though they look different, they are the same. All right, so let's move on. So there is one thing that can change this rule, okay? And that one thing is that if you're looking at an open system, now open system simply means that it's in the open air. So if you were to look right here, and if you were to, for instance, burn a piece of wood, and you weighed that wood before you burnt it, hopefully you remember from our chemical reactions lesson is that there are some indications of a chemical reaction. One is that there's a temperature change, a precipitate, or gas being given off. In this case, we have temperature change and gas being given off. So when you burn the wood turns to ash, and then you release smoke. Because you're releasing smoke, that air is escaping, and that air has weight to it. Remember when we did the baking soda and the vinegar in the class and we weighed them out? Well, because you're losing some of that gas, the weight of the ashes will go down. And so in an open system, okay, in the open system, here's where it gets really weird. In an open system, the law of conservation is change. What does that mean? It means that because you're losing weight, if you were to weigh the ashes up, they're going to weigh less than the log did. Okay. However, if you were to go ahead and somehow catch all that smoke, collect all the ashes, and then weigh them together, then they should equal out to your weight of the log. That would be a closed system. In a closed system, nothing escapes. The air, or if you want to say the gas, everything is captured and measured. And because it's captured and measured, the law is exact. Okay, so that's a big deal. In a closed system, we can measure all these parts that would go flying about the place. And because we can measure all of them, what you begin with will be what you end with. Okay, so keep that in mind. Now, the next thing we talk about, let me stop this right quick. The next thing we're moving on to is the law is how to balance them off. Now, we'll be looking at that in a separate video, because I don't want this one to get too complicated as we move on. So, lesson for the day. If we're looking at all this stuff here, is that, hey, the law of conservation says what you begin with or your reactants must equal your product. We now have hopefully revised looking at what these coefficients, what they mean, and these subscripts. And if you did your ed puzzle before this video, that will make it so much easier for you to understand the words coming out of my mouth. Now, the cool thing for you guys is that you don't have to balance equations off. They sort of changed that in the last few years, but you do have to recognize when an equation or when a chemical reaction is balanced. So we'll be looking at that next. All right, so look at here at your example. So here we have our reactants, which hopefully you're identifying as your beginning, and your products, which you end with. So we're going to start with some word problems. So if we were to put some magnesium into a container and we would add it to oxygen, which oxygen is a necessary fuel for burning, what is the mass of my reactant? Okay, so for this one here, we're going to say, oh, that's pretty easy, Mrs. Smith. That's super easy. give me easy stuff. That's going to be 46.8. How do I know that? Because it tells me the weight of it. Okay, and what's the mass of my product? So 46 would be magnesium, and 32 would be oxygen. Okay, grams. Put it right. So, yeah. Now, what's the mass of my product? Well, also given to you, 80.6 grams. There we go. So, pretty easy stuff. Now, what's the total mass of the reactants? So this is where you'll do math. You'll say, okay, I got to come here and I got to add a plus sign because it's a plus there. So you would say 46 plus 46 by 8 plus 32. Okay, and then you add those up. So if you're looking at this one here, we're going to say, okay, that is also 80.6. Okay, so in other words, when we added up everything, it equaled the same. So here comes your next question. Does this experimental data support the law of conservation of mass? We're going to say, oh, of course it does, Mrs. Smith. Why does it? Because whatever I started with is what I ended with. So we're good to go. Okay, so let me clear this stuff off. Believe it or not, that would be an EOG level question in terms of is using the information they give you to answer the question off. Let's do another one. So we have magnesium plus oxygen, and it ended up to combine to form magnesium oxide. So this is our reactant, this is our products. And so based on the law of conservation of mass, predict the minimum amount of magnesium you need to react with oxygen to produce 40. So this is where your math skills come in really great. So we're solving for X is pretty much all we're doing. We're saying that we're ending, okay, it's nice and big. So whatever we have, it must end or equal to 40.3. Equal to 40.3, right? All right, so that's easy enough. And then we know that some of this is 16. So the question is, if we are ending with 40, we must begin with 40. So we're going to say what plus 16 equals 40. And so in math, you learn that to solve for X, you would take one number over the equal side and change the mathematical symbol. So you could then say, hey, 40.3 minus 16, and that should give you your answer. And it would be 24.3. So the answer here would be 24.3. So 24.3 plus 16 gives me 40. Whatever I end with must equal what I begin with. So in this question here, all you're doing is solving for the X or solving for the missing amount, understanding that, hey, they must be equal. Both sides of this equation must always be equal. Okay, let me erase this and then we'll do one more. So in this one, guys, we're looking at sort of the same thing. I'm starting with 12.2 grams of magnesium, okay, 12.2, and I am adding to that 8 grams of oxygen, okay? So in other words, it's saying that assuming that magnesium and oxygen will react completely with each other. So there's a full reaction, it burns up, it gets really bright, and then you're creating this product called magnesium oxide. And if it's a closed system, how much magnesium oxide will you make? Well, once again, whatever I begin with, I must, hopefully on your brain saying, end with. And so we now know that if you add up 12.2 to 8, you get 20.2 grams. So here would be 20.2 grams. I'm not gonna write that one down, that's pretty easy. And here's the last one. So we get 46 grams of magnesium, and we're gonna add to it 50 grams of oxygen. Okay, now when this reacted, it created 80.6 grams of oxide, magnesium oxide, but there's still some X, there's still some oxygen. So the question is, how much oxygen is going to be left over? So once again, whatever you begin with, you must end with. So if I started off with 48.6 grams of oxygen, and I react that to 50 grams of magnesium, 50 grams of oxygen, hopefully somewhere that some of you got your calculators out, or if you're good in your brain, you said, hey, Mr. Smith, that is 98.6 grams of reactant. So if I'm starting with 96, I must end with, drum roll please, 96. But over here, I only have 80. So you would say, oh, well, if I only have 80 of magnesium oxide, the other part of 98.6 must be the missing oxygen. So then you simply say 98.6 minus 80.6, and you come up with 18 grams of oxygen. So guys, that's how, 18 grams. There we go. So that's how we're looking at law of conservation of mass. Now, this is really important in engineering and chemistry, because when they're combining elements, when they're trying to figure out how much metal they need to make the steel or to extract different stuff, you got to know what you want to end with or what you're beginning with, and see what that loss is inside the chemical reactions. Because every time you lose elements or you lose compounds, that's a money being wasted or money that's going into the atmosphere. So this is a really big part of chemical engineering and even somewhat mechanical engineering, which pretty much makes all the stuff we have on our planet. So we'll go into level 3 tomorrow, the next time we have a lesson, and finish this lesson off. I hope you guys learned something. And if you have any questions, remember, you can always contact me.